about how magnets and magnetic materials work a little bit. So Knight talks about this, but just real briefly. So all magnetic fields are created by moving charges. Okay, so we've seen a bunch of examples. We've seen that if you have a current, it causes a magnetic field. Well, basically all magnetism comes from moving charges. And so here's an example. If you have an atom, if you have an electron, okay, going around the atom, it's a little current. And so what you have here is you have a little magnetic dipole. We talked about this last section, a little magnetic dipole. And so this is where the moving charge is. Now, in reality, this is true, but in reality, in most atoms, there's a whole bunch. Here I have a whole bunch of sort of electrons moving around, and so this effect tends to cancel out. All right, and actually what's the stronger effect is what's called the spin of the electron. And you've probably heard about this in chemistry class or maybe in an older physics class somewhere. But all electrons have what's called spin. And in a very general sense, we sort of imagine that the electron is rotating about its axis. Okay, so the electron has a negative charge. It rotates about its axis, and this is what we call the spin. Now, in reality, spin is something different than this. And you can't actually explain spin in terms that make sense classically or mechanically. It's a quantum mechanical effect. All right, but it basically has the same effect as if the charge was spinning. And what it really does is if you're a charged particle spinning around, you're a little microscopic magnet. So each electron is a little tiny magnet. Now in most atoms, if you know anything about chemistry, each energy level is filled with spins and they're in opposite directions. So if it's a filled energy level or a filled energy level, basically those two spins will cancel and there is no net magnet there. Okay, the two dipole moments basically cancel out. All right, so what can happen though is in any atom that has basically one partially filled level, you have one extra electron and one extra little tiny magnet. Now in general, like in this picture here, these magnets are kind of just misaligned, so they don't do anything. But in some materials, like iron, okay, these magnets tend to line up. And so we call these kind of materials ferromagnetic. And ferro is just a word that means like iron. And so a general piece of iron that's just sort of hanging out will look like this here, and it has what's called magnetic domains. And so these are little regions where basically like right here, the spins tend to line up, so it's a magnetic field going down. Here they tend to line up, so it's a magnetic field going to the right. But what happens is if I put an external magnetic field from something else here, these domains will tend to line up with that magnetic field. And here's an example of this. So here I have a piece of iron on the right here, so a piece of iron or something that's ferromagnetic, and here I have a solenoid. And so the solenoid is set up, and so that this is like the north and this is the south. All right, and so what it does is it's a magnetic field makes these domains line up like so, and so this little magnet is basically kind of like this iron then becomes a magnet. It's like north and south, and basically this is making each little extra electron line up with the magnetic field. And so since this is a magnet with a south pole here and this one's like a north pole here, they attract. And so this is how magnets are able to pick up pieces of iron like paper clips. And pennies, for instance, don't work that way. They are not a ferromagnetic material.